Peijin, and together with my co-author Minzhou Wang, we will be presenting our work, AI-driven peripheral devices management, and assistive multimodal input for wireless human-computer interaction. Today, we will show our work and how we build on existing effort while filling a critical gaps. Our focus is on making peripheral devices use more efficient and inclusive, creating a unified AI-driven platform that benefit both mainstream and disabled users. Let's start with the problem. Traditional key binding systems are complex. Users must go through trial and error to configure devices, which increase setup time and errors. For people with disabilities, simultaneous multi-key operations are often impossible. Existing adaptive devices, like eye-tracking hardware and adaptive controllers, they help, but they're expensive, platform-specific, and hard to configure, so adoption remains very limited. There's a clear need for an integrated, AI-driven cross-platform solution that reduces setup complexity while broadening accessibility. Our hypothesis is that by combining modular and linear key binding structure with AI-driven layout, optimization, and voice-based input, we can improve efficiency, accuracy, and accessibility. This approach should reduce cognitive load, streamline setup, and enable inclusive, multimodal interaction. Importantly, it benefits not only the disabled users, but also mainstream users who want faster and easier control. Our idea is not just to improve accessibility, but to demonstrate that accessibility-driven design benefits everyone. By reducing cognitive load, AI layout and voice input make control easier, faster, and more enjoyable for everyone. Human-computer interaction today struggle with three big issues. Trial and error key binding takes too long and causes errors. Disabled users can perform multi-key actions, so that limiting functionalities. And cross-platform inconsistency force users to reconfigure from scratch. Competitors like Xbox adaptive controllers, Sony access controllers, and tools such as Project Ares and GameFace, they address part of this, but they are hardware-heavy, expensive, and platform-specific. This gap shows the need for a software-first, AI-driven approach that scales across devices. For example, the Xbox adaptive controllers works well for console users, but its high price and limited ecosystem make it hard to adopt widely. Tools like Project Ares bring impressive eye tracking technology, but they require tedious calibration and often struggle in fast-paced gaming. This causes highlight the tension. There's strong innovation in the field, but each solution remains isolated. What's missing is a unified cross-devices approach that can scale. As mentioned, competitors have values, but also clear limitations. Adaptive controllers is customizable but costly and limited to a few platforms. Eye tracking and facial tools is calibration heavy and narrow in scope. Voice system is useful but not integrated with gaming or multi-key action. Our work is distinct because it provides a software-level AI-driven approach, use modular and linear layout, integrated multi-modal input, and importantly, build a cross-devices web-based platform that is accessible to all. This pattern highlights why we choose a software-first approach. By separating ourselves from the hardware, we are not tied to a single platform. That means a gamer, a designer using shortcut-heavy software, or even a student learning with digital tools can benefit from the same framework. Our goal is to make accessibility mainstream, not niche. We identified three key challenges. First, real-time performance gaps in accessibility tools. Second, high setup complexity and heavy learning burden on users. Third, lack of cross-platform consistency and adaptive framework. This challenge persists because accessibility tools are often afterthoughts. Developers prioritize performance, but not inclusivity. And we saw our solutions are built. They're isolated in specific ecosystem. Without a unified adaptive framework, progress stay fragmented. Our solution aim to address this head-on. Our first solution is modular and linear input. Instead of traditional free design method, we use predefining building blocks and step-by-step sequence. These include temporal elements like hold until release or single quick trigger, which let users configure complex inputs much faster and more intuitively, without trial and error. The benefits are clear. It reduces setup time and cognitive load. It ensures layouts are consistent and cross-platform. And it's easy to use, even for people with no programming background. What's powerful here is that this approach works for everyone. For disabled gamers, it opened up actions that were previously impossible. For mainstream users, it simply makes setup quicker and more efficient, proving that accessibility-driven design can benefit all. The second solution is adaptive AI layout generation. We use machine learning to analyze interaction patterns, like timing, frequency, and ergonomics, to create optimized layout. The AI groups related actions, minimize hand movement, and reduce reaction time. This is similar to how modern smartphones suggest text predicts. The AI adapts to your habits. Here, the AI learns which key you use most often and place them in an optimal position. Over time, it refined the layout to minimize hand movement and improve response speed. This evolution transformed what used to be manual trial and error into a smart, supportive process. For users, this means layouts that are more efficient, comfortable, consistent, enhancing performance while reducing cognitive load. Our third solution introduced Voice AI Assistant. Voice assistants are now part of our daily life. Siri, Alexa, Google Assistant. Users already trust this system for commands like sending messages or controlling lights. Extending this into gaming or creative works feels natural. For example, saying reload or switch layer is faster than thumbing for multi-key combos. Here, speech recognition maps spoken commands directly to macro or multi-step actions. This is particularly valuable for disabled users who cannot perform simultaneous key presses, but it also makes executing advanced commands easier for everyone. By combining physical input, AI layout, and voice, we enable truly inclusive, multi-modal interaction.
Have some interesting. Okay, sorry for the interrupt. Thank you, Peggy. And we are going to discuss some experiments for this study. Our goal is to test how effective the AI-driven platform is and what kind of value it's going to be give to the users. We do this through the control experiment. For the game context, we are going to use Crossfire, and this is a first-person shooter game with many fast and complexity actions under time pressures. The players, they are going to need some moves, fights, or they need switch weapons, and also gonna do some functions like chatting, or they need to take some screenshots. Also, the game rely heavily on the shortcuts and key combinations, and this make it an ideal testbed for our study. And we conducted 2 experiments to test our approach. The experiment 1 is comparison of the key binding method. In the study, we compared 2 ways of creating key bindings. The experimental method used a modular and linear approach, and the control method is going to allow the players just to do the free design their own bindings. We recruited 12 gamers, average age is 24.3 years old, and they have 7 males and also 5 females. So the task has 3 parts. First, the players, they're going to set up 10 key bindings for essential FPS functions, such as move, attack, reload, or open the map. And next, they're gonna complete 30 random trails where the system's gonna be promote a function and they need to press the key assigned. And third is they need to fill out the short evaluation. When they finish all of these, the evaluation is about easy of use and satisfaction. And we measured the setup time, we measured the consistency, the accuracy, and the certification. And we also expect the experiment method to reduce some setup time from 5 minutes to under about 3 minutes, and increase accuracy from 50% to at least 70%, and also raise the certification from 3.2 to 4.2 out of 5. And experiment 2 is we are going to evaluate the AI optimized layout. The second study is focused on the layout optimization, and we compared the player created outlines with the AI optimized layouts. Again, the same 12 players, they participate, and each of them gonna perform the same game tasks in, there are gonna be 2 10-minute sections. So one with their own layout and one with the AI layout. And during the section, we track data continuously through some keystrokes and gas analysis. These key metrics include, first, completion time. They expect to increase from about 8 tasks to 10 tasks. And next is keystroke count. Expect to drop from around 120 to 100 or fewer. And key intervals, it expect to improve from 1.5 seconds to 1 second. And also the gas point concentration, expect to become more focused. We assume we can drop that from 70% hotspot coverage to about 40%. And finally, the subjective ratings expected to raise from about 3.0 to 4.0. And together, these 2 experiments, they can test both the setup process and the optimized layout. They show how structured method and AI support can improve the efficiency, accuracy, and user satisfaction in gaming. And in the experiment 1, we compared the modal key bindings method with a traditional free design method. So the result, it clearly showed the modular method is faster, it's more accurate, and it can be better received by the users. First, in terms of the setup efficiency, they need about 5 minutes to set up and finish the game in the free design condition, but they only need 2.8 minutes with the modular method. So most of them, they comments like the modular method is give them a more clear logic and reduce unnecessary trial and errors. And second is usage and efficiency, also accuracy, they improved. With the modular method, average reaction time that was about less than 1 second compared to the 1.47 seconds in the free design, and accuracy was also higher, 90% versus 81%. And these results suggest the structured method help the users, they respond faster and they make the task more easier. Finally, is the subjective ratings confirm these findings, like the free design conditions scroll lower around 2.4 or 3.6 on a 5-point scale, while the modular method is scored consistently higher from 3.6 to 4.6. and the participant they especially rate it as more organized, more reliable, and more controlled. And in the summary, the moderate key bindings method, it outperformed a free design in every dimension. It made up the setup easier, made up setup quicker, improved the consistency, the accuracy, and also seen as a clear or a more reliable methodology. And in the second experiment, the same participant, they performed the identical 10 minutes game tasks under both baseline and the AI optimized layout. The AI layout clearly improved the performance. They complete about 10 tasks and compared to 8 with the baseline, and the keys drops, it dropped down a lot from 121 to 97. And if you look at the screen, we use the gas recorder, and the gas recorder analysis showed that the visual hotspots shrink from 61%. So the keyboard area that was 38%. So the players focused more on the essential keys, and the participant they remarked that the AI layouts let them be more concentrated and can be more better and reduce some unnecessary scanning between those keystrokes. We also measure the subjective ratings using some symmetric differential scales, and the basic layout is scored relatively low, most of them between 2.1 and 3.8. So, and also the weakness area was the organization and positions, because they describe it's take more time and it's more messy and can cause more error. Easy of use was kind of low from 3.2 to 3.3, shows a limited usability. And in the contrast, AI improved the layouts. It scored much higher, between 3.9 and 4.5. It strongly improved the appeared in the efficiency, the accuracy, and reliability. And participants, they also rate it as more intuitive, more relaxing, and more helpful. These results show the AI layout not only just improved the performance, but also gave users a smoother and more confident experience. And our experiment confirmed both modular and AI optimized method. They significantly improved the user's performance. This method and with a time dimension, such as I'm gonna hold this key and until I release it, or there will be a single quick trigger. It allows users to think of actions conceptually instead of just learning by trials and errors. And the layout also made AI easier to find and reducing some search time, hesitation, or errors. Just put this together, and those gonna be lower the memory load and enhance the usability. And in terms of user experience, some participants, they did report discomfort at first, saying it was hard to locate some new key positions or memory some new key positions. But this challenge, it faded really quick as they formed the new habits. But overall, the results suggest that while the adaptation is required, the learning curve is required, but it's kind of short. But also the method can bring some more performance and usability benefits. And our limitations we observe as a potential relearning cost if AI-driven layout or something, or the macro, they update too often. So the users, they can become more frustrated if they consistently have to adapt to a new configurations, but which could reduce a long-term usability. And this highlight the layout stability is just kind of important as optimization. But looking forward, the future system could balance adaptivity and stability, which also can allow progress update or giving the users the option to lock certain key options, key positions. And beyond the gaming, this approach can be a potential in creativity and professional fields, as well as in education or accessibility, by adding some adaptive learning mechanics. So the layout, they can become more personalized and can be evolved with the user's long-term habits and needs. And thank you for listening, and